Yeah, you can start.
So good evening, everyone. A very warm welcome to today's session. Today is the second day of two-day talk series on linear group delivered by Professor Amber Habib, Professor and Head of the Department of Mathematics, Shiv University, School of Natural Science, Uttar Pradesh. Today's session will be a continuation of yesterday's session. We are very happy to have today's session chair as Dr. Pradip Kumar. He is an assistant professor at Department of Mathematics, Shiv University. He did his MSc from IIT Kanpur and PhD from Harishchandra Research Institute, Allahabad. I welcome Professor Amber Habib and Dr. Pradip to today's session. Last but not least, I welcome all of the participants. Over to you, Pradip, sir.
Am I audible? Hello?
Yes, sir.
Yeah, thank you. Thank you, Kari Leaf, and very good evening to everyone. And thank you for inviting me to chair the session. Also, I congratulate Kari Leaf for such excellent initiative. I have seen many YouTube videos and was so really impressed the way you people are really doing. And it's really an honor to chair Professor Habib's session. Being an MTTS alumnus, I always feel an emotional connection with the name MTTS whenever and whichever form it comes. I think we all share the same feelings. So it is really a great opportunity for me to connect with all of you. Let me share you one thing about Professor Habib. So I don't know whether Professor Habib remembers it or not. So this was November 2013 event when I applied SNU for the faculty position and went for lunch with Professor Habib and other colleagues. At some point, we started talking about MTTS. And when I heard that Professor Habib is associated with MTTS for a long back, I immediately felt a secure connection and thought if such a person is heading the department will for sure respect the value of math education and will have respect for the research. From last 7 years working with our head of the department, Professor Habib, I can surely say I was right. So he's a really great listener. He has a great sense of any kind of mathematics. You can go to him and talk any type of math. He has really good sense, even if the topic is new. His comments are always super, and we always learn something every time after discussion with him. Apart from the mathematics, he has really good sense of academic justice that cannot be written in a rule book. We are fortunate to listen to you, Professor Habib. So there are a lot of things to say, but I think without wasting time, I will invite Professor Habib to start the sessions. Over to you, Amber, sir.
Well, thank you so much, Pradip. I do remember all the faculty hirings very clearly, especially when we have selected the people. Yeah. Okay, yeah, but thanks for those very kind words, and yesterday Satya also for what he had said. And again to Kari Leaf for organizing this and inviting me here. As Pradip said, it's just a delight to do anything associated with MTTS, to have anything to do, whether as participant or as audience.
Surely.
Okay, so now it's the second lecture. So let's look at some of the key features from the first lecture, right? Let's start with that because there was a fair amount of stuff that happened. We can't really be expected to remember everything from it after first exposure and at short notice. But let's look at some of the highlights so that we can try and take them forward today.
Priya, can you take it?
Hello?
Yeah, yes.
Okay, Priya, you want to do that?
Everything is fine.
I would be happy if you did that.
Okay, sir.
I would like to see your summary.
Okay.
I will learn something that way.
So like yesterday, we were talking about linear groups. So we are working on field R. So we first started with MNR. So MNR is set of all n by n matrices with real entries. But we know all those matrices are not invertible. So we can consider the set of all invertible matrices, that is GLNR. So these are the space that we are interested in. Now we can define a norm on MNR, that is the operator norm. So how we define, we are connecting actually, we have to define a norm on metrics. So we already have this Euclidean norm. So we are somehow trying to connect the Euclidean norm and to get a norm on matrix. So we define this operator norm on a matrix as a operator norm of a matrix A as supremum of norm AX by norm X, where X is not equal to 0. So now we can check it's actually a norm. So we got a norm on a group of matrices. So we can define a metric, that is the metric induced by the norm. So we are happy. We have a space with a metric. So we can define the closed sets, open sets, continuous functions, and everything. So for example, if we consider this determinant as a function from M and R to set of all real numbers, then it's actually a continuous function. So from that, what we can see, if we consider GL and R, we need to know whether GL and R is open or closed. So we can actually construct a function from M and R to R, which is actually a determinant function. And what is GL and R? It is actually the inverse image of R minus 0 with this determinant function. So in R minus 0 is open. So and determinant is continuous. So inverse image of open set is open. So GL and R is open in M and R. So this is the advantage of getting a metric on group of matrices. Now we have this definition of matrix group. So what is a matrix group? This is a closed subgroup of GLNR. And of course, GLNR is a closed subgroup of GLNR. So we know GLNR is a matrix group. So the general definition is a closed subgroup of GLNR. Now we can define the linear group. So linear group is actually a group which is isomorphic to matrix group. Now we have this two groups, G and H, that is two matrix groups. Then we can define the homomorphism between these groups. So how we define? First, that phi is a group homomorphism and the phi is continuous and phi of G is closed in H, that in the target set. So we have this group of matrices. Now we have this norm. So we have this metric. So we can talk about limit, continuity and all. Now the natural question is, can we do calculus? So for that, we consider Rn square and we consider a subset that is a matrix group. And for a element in matrix group, we define the tangent vector. So if we have a tangent vector, we can find different types of tangent vectors. So we can consider the set of all tangent vectors. And then we proved this set of all tangent vectors of this I is actually a vector space. So that we did yesterday. Now, later we did this matrix exponential, that is how to define e power a, where a is a metric. Then we actually intuitively, we first observe a result that is determinant of e power a is actually e power trace of a. Then we kind of prove that result. And we observe that is immediate in when the matrix is diagonal. And then we use this fact and actually prove that determinant of e power a is e power trace of a. So that's what we did yesterday. Thank you, sir.
Okay, that was impressive. I mean, I would find it very hard to do what you just did. I would have to be writing it somewhere to talk to people. Okay. Anyway, thanks. So now let me share my, my tablet and let's get going. Okay, so we have already had this review, but as I said, I like to see things written down as well. And it's good if you see something 3 or 4 times. So I won't bother to read through it, but if you scan through it, you will see that Priya has actually given a few more details than I have put down. So that's also good. Right. So you define these, take these matrices, they put a norm, put a metric on them, take the invertible matrices, define the matrix group as closed subgroups. Here's a couple of examples, the ones with determinant 1, which is called the special linear group. The orthogonal matrices, they form the orthogonal group ON. The special orthogonal group, which is the orthogonal matrices with determinant 1. We saw yesterday why these are all closed subgroups of GLN. Okay. And more generally, any group that's isomorphic to a matrix group is a linear group. Then you define matrix group homomorphism. I did want to remind people that one very interesting question was asked at the end last time. So I put it down in red as a reminder, which was, okay, so I want a group homomorphism which is continuous and has a closed image. Okay, so is it possible that there is a group homomorphism which is not continuous? And I said this reminds me of something, and I talked about some situation, and only later I realized that my mind had actually done the right thing. That situation is actually it's not just something related, like I said, it's exactly the kind of example to look at to create, to see a homomorphism which is not continuous. Because look at R as an additive group, right? Then a homomorphism is something so that phi of x plus y is phi x plus phi y. And the question is whether just this additivity condition is enough to force continuity. And the answer is no, it's not, but it's a bit tricky to come up with an example. But here's a hint that look at real numbers as a vector space over the rational numbers. Okay, look at that situation and then see what you can do. Okay, and one could also ask, okay, suppose there is a group homomorphism and it's continuous. Is it possible that it doesn't have a closed image? So yes, it is possible that it doesn't have a closed image. That question was not asked, but it's the natural next question to ask if you have asked the first one. I'm not going to get into and the second one is actually pretty easy to answer, but I'll not do it right now because I want to give the main story. But if this second question looks interesting to you, you can ask me about it at the end of the lecture. Okay. Now, what else did we do? We talked about tangent vectors and we defined them as the derivatives of differentiable curves, C1 curves, right? And we said that you look at all the possible tangent vectors at a point that will be called the tangent space at that point. Now the tangent vectors, and if you take any subset of Euclidean space, you can define tangent vectors like this. There's no reason in general why they should form a vector space, but in this case they do. It's automatic. If you have a group and you look at the tangent space, if you have a matrix group and you look at the tangent space at a point, the tangent vector at a point, they will form a vector space. We just checked it for the tangent space at identity. But similar proof can work at any point. And the other thing that was observed as, actually as a response of mine to a question that one of you asked, that if one looks at the whole GLN and says what is the tangent space to that, then it's really all the n cross n matrices. Because GLN is an open subset of Mn, so locally it's completely filling Mn, right? Around identity, everything which is close to identity is actually invertible, is in GLN. So it's actually filling out Mn close to identity. Therefore, the tangent spaces are all of Mn. So there's an identification like this. And that is something I want to refer to today. Then we started talking about the exponential map, and we said that you would define it through a power series expansion, just as we do for numbers. There are issues of convergence, but with the help of the operator norm, they can all be sorted out. And I would just like to leave it at that, okay? But we did compute some specific 2x2 examples just to see how this works. And as Priya recapped, we proved that the determinant of the exponential is the exponential of the trace. In this, on the left-hand side, you have exponential of a matrix, but on the right-hand side, you have your ordinary exponential of a real number. And one implication of that is that since this determinant is the exponential of a real number, therefore it's not zero. And therefore this e to the a is an invertible matrix. So exponent is actually a map from Mn to GLN. Okay. Okay. All right. So that's about what we did last night. Now let's continue and try to understand this exponential map a little bit more. Yeah. So now of the regular exponential map, exponential of real numbers, one of the key, or maybe the key property is this one, right? That exponential of x plus y is exponential x times exponential y. And so naturally we wonder whether this will work for matrices. Well, to look at that, maybe we should really know why this works for numbers, and then we can see whether that argument can be applied to matrices. And if it can't fully be applied, can it partially be applied, right? So rather than just looking for examples or proofs, let's do one thing. Let's see what the argument was, for numbers, right? So how does it go? Here is one way. you start with e to the x and e to the y. You write out the definitions. Okay. Now what you have is you have some powers of x, right? Some combination times some powers of y. So you'll be multiplying them with each other. So what you do is you collect the same powers. Okay. So meaning when the sum of the collect the terms of the same degree. So for instance, take x cube and y cube and put it together with x cube y squared with x to the 4y, right? So put all the degree 5 terms together, put all the degree 4 terms together, and so forth. So this will lead to a sum where the main thing is over the possible degrees. So let's say that that is some k, and that can go from 0 to infinity. And then let's look at how terms of some degree k can be created. So there'll have to be an xn and a ym such that the n and the m add up to k. Right? So I can say, all right, there'll be some x to some power, and then the y power will have to be k minus n, right? So that the total is k. Now this x to the l has to come from x to the l by l factorial, right here. And this y to the k minus l has to come from this combination, okay? And how many can you create? Well, you can create with L going from 0 to k, right? And then automatically k minus L will also go from 0 to k. Okay. I'll just do the steps first, and we will do some finer worrying about the reasonings later. Okay. Okay. Now here you almost have, an NC, a KCL kind of situation. L factorial, k minus L factorial are the right things from the denominator. K factorial is missing. Let's put it in. So nothing very much happens in this step. You simply multiply and divide by k factorial. So you will get, but then k factorial, L factorial, and this simply becomes k choose L. And you have x to the L and y to the k minus L. Now what you do, you look at the second summation and you realize this is just the binomial expansion, right, of x plus y to the power k. And then this, of course, is e to the x plus y. Okay, so that's the argument. The first step does need some justification because you are taking an infinite expansion and you are rearranging the terms. But that has a justification, and especially because these are power series, one knows that this is allowed. This is the Cauchy product. And whatever reasoning you use, you can extend it to matrices. So that first step is okay. All right. Nothing much happened in the second step. But when we apply the binomial, right, what are we doing? Right? What does this need? This needs the fact that x and y commute when you multiply. Right? Suppose you say a plus b times a plus b, what you really get is a square plus ab plus ba plus b square. The only reason you write 2ab is because ab and ba are the same thing. So the binomial expansion depends on this. And now you can see that with matrices, this is where we will run into trouble. If I give e to the a times e to the b, a and b may not commute. If I try to copy this proof, I will fail at the step where I want to apply the binomial expansion. On the other hand, if they do commute, then every step goes through. So at least I have a partial result. Okay. Which is that if you have two n cross n matrices which commute with each other, then in fact you can make this assertion. Okay. Okay, and when they don't commute, anything could happen. By chance, sometimes this may still work, but generally it won't. Okay. And if you want an example where AB, and so you don't have to do much, just take any simple example where A and B don't commute. I think this will work. Okay. So these two don't commute. Okay. And if you were, now we all actually more or less did all the required calculations yesterday. So if you look at those calculations and applied them to this example, you will very quickly see that these two are not matching up. Okay. So it doesn't always match, but when they commute, it matches. Well, this is itself good for many things, all right? So it's not therefore perfect. This exponential map is not a homomorphism, right, fully, but it is partially, and that partial aspect is still very useful. Let's see some of the things we can get from this, right? So some things definitely commute with each other. For example, A and minus A certainly commute with each other, right? And therefore, if I look at e to the A and e to the minus A, it will be E, A plus minus A. Therefore, e to the 0 is the 0 matrix, and that gives you identity. Okay. And what does that tell me? That tells me these two matrices are the inverse of each other. Well, I already knew that e to the A is invertible, but what has happened now is that I have learned what the inverse is, right? The inverse of e to the A is simply e to the minus A. Okay. And one could have actually made a more general statement. Take any multiple of A, any real multiple, and any other real multiple of A, they will also commute. So A and minus A was a special case. And what you can see from here is that if you multiply these two, then you are going to get E, then SA plus TA, so S plus T into A. Okay. Okay, and this one can view as creating a certain homomorphism. So consider the following map. Fix some A and define phi of A, sorry, phi of T to be exponential of TA. So what is this phi? This phi is a map from R to GLN, right? Because these are all invertible matrices, right? And this, so this is now actually giving me a curve in GLN, right? And phi of 0, of course, is identity. And what is the derivative? You can probably guess, right? The derivative will be A. Okay. So, for example, look at the original definition, right? And say what is e to the TA, so you'll get t to the n. Differentiate, and differentiation will work in the usual way when you differentiate with respect to t. So all the powers come down, you put t equals 0, right? Only that linear term survives, just as usually happens with e to the x, and you get this as your derivative. Okay. All right, that's okay. That's going to be very useful because suppose I was in GLN and I wanted to work with a particular tangent vector. Now, there is an easy way to do it, which is to simply take the straight line in that direction and its derivative will be this tangent vector. But what we are seeing is that there's another way to get the same tangent vector. Okay. I could simply take tx and differentiate that and get x, and that's fine, right? That's one simple way to do it. Okay. There is a less simple way, which is this one, which is that you take exponential of tx and differentiate that. That will give you the same x. Okay. But the advantage of this is that this is a homomorphism from R to that, right? So there is more structure available when you work with this curve rather than when you work with the straight line, right? This relates addition in R to the group operation, right? So there's a more special curve available to work with. Okay. Right, let me see what's the next thing I should tell you. So this is fine. Okay. Now, what have I got? I've got the exponential map from Mn to GLN, and GLN, remember, is anywhere in Mn and it's open there. Okay. we could be interested in what is, the derivative of this exponential map. Okay. All right. Now, what is derivative? So, one way to understand derivative. Well, I hope you remember that in calculus of several variables, if you have a function between two Euclidean spaces, then the derivative is a linear map between them, right? So if you have domains in two vector spaces, the derivative is a linear map between those vector spaces. So in this case, Mn is anyway in Mn, but GLN is also in Mn, right? And filling it up. So the derivative will be a map like that. Depends, okay, wherever you differentiate, let's say that I will differentiate at 0, right? The 0 member of Mn. Okay, and you'll get a map like this. Okay. Now, how do you understand this? So, right, how do you figure out what it is going to do to a particular matrix? And the answer is that simply take the directional derivative in the direction given by that Mn. Okay. I mean, that is how it works in calculus. So we simply are repeating this basic several variable calculus here. Okay. So, all right. So what will we do? We will take this and we want to see what it does to some x. Well, we have to take this function, apply it to a curve, right, which was creating this x. Now you want the directional derivatives. You actually want to work with the straight line. You want to apply the function along this straight line and you want to differentiate this. Okay. And we wanted to do this at 0. But we already know the answer, right? The answer is x. Okay. So we see that the differential of this exponential map is just the identity map. Differential at 0 is just the identity map. Okay, so that's again a nice thing about the exponential function. And one consequence of this is the inverse function theorem from calculus can again be applied here. Right, and remember what it says, the inverse function theorem says that if you have a differentiable function and if the derivative is invertible at some point, then the function itself is invertible, maybe not fully, but at least locally, so that it's locally invertible. Okay, so therefore we learn this about exponential because its derivative is in fact just identity. Okay. So one says that it's a local diffeomorphism at the origin. What does local diffeomorphism mean? Exponential, of course, is a differentiable function. But what the inverse function theorem is telling us about it is that locally it will have an inverse, and that will also be differentiable. Okay. And having it locally means so this is the situation. Let's say here is Mn, here it's 0, and here is my GLN. There is identity where I'm taking this tangent space. Okay, and what are we saying? That there'll be some open set around this 0 and some open set around this GLN. I mean, around this identity in GLN, right? And you have the exponential map going like this, so that the exponential map will exactly match, exactly take one to the other. And plus there will be an inverse. Okay, and what we do with this inverse, of course, we naturally will call log, right? I mean, that is the natural name for the inverse of an exponential function. And incidentally, you could also do this by working directly with power series expansions, right? The power series definition of exponential could also be used to actually come up with what is the inverse of this. But we won't bother with that detail today. But we are getting some sort of picture that if you look at the invertible matrices, there is a nice map connecting them to the set of all n cross n matrices. Okay, that's the exponential map. Right, and we remember what is our philosophy. I think I got to say something about this, that when you have a tangent space, you want to be able to think of it as locally being a good match to the actual object, so that some non-linear things can be approximated by linear things, right? And so this could work for curves, it could work for surfaces. I mean, with tangent plane, it's the same idea. And we want to extend that to our group situation. The group is something curved, non-linear. This is something straight. Locally, this approximates this through this exponential map in this neighborhood where there is a local diffeomorphism. Okay. All right, now those are all the things that are working out with GLN, but we don't only want to work with GLN, we want to work with any matrix group. So the question is whether these things will work. If I go to a closed subgroup of GLN, will I still have some nice setup like this? Now I'm not going to prove this, but I'm just going to give you the fact, okay? But having understood this part well, I hope that you will not have difficulty accepting what I'm going to say now. It should at least look reasonable, okay? Proofs involve some work, so there's no way I'm going to try to do those proofs today, okay? But at least this, I think, serves as sufficient motivation to guess what the situation should be. Okay. All right, so let's take a matrix group. So it's a closed subgroup of some GLN. Okay. And look at its tangent space at identity. I will use this sort of funny little g to denote that. This, okay. So this is the tangent space at identity. We have proved that this is a vector space, so that is fine. Now this is going to be some subspace of Mn. So the question is, how do we know whether some member of Mn belongs to this particular subspace or not? Okay. So first, there's a nice test for figuring out whether some x belongs to this tangent space or not. What you do is you look at its exponential, but not only exponential of x, but exponential of all multiples of x. And you ask whether they belong to the group or not. And the result is that, well, the thing will be in the tangent space if the exponentials of the line through that x fully lie in the group that you want to work with. Okay. All right. So that's one thing, right? And now, once you have this, then certainly exponential is taking this tangent space to the group, right? In particular, because when t is equal to 1, then in particular e to the x belongs to g. So exponential is such a map from little g to capital G. That's coming from the first part. What kind of map is it? It has all the nice properties that exponential had when you were looking at the relationship between GLN and Mn. It is a local diffeomorphism. At 0. So this picture that I had drawn also works for any matrix group and its tangent space at identity. Okay. Okay, so this becomes a way of going between a group and its tangent space. And this becomes a way of converting group questions to questions about this vector space, and therefore converting certain group theoretic questions to linear algebra questions, okay, to matrix operations. And I will do an example in a bit. Let me see, can I do it right now? Well, I can, but let me give you one or two definitions first. Okay, and then we will see one application of this. Okay, that's relatively simple, but it will still be a little involved because we are trying to do it without knowing any of the grand abstract theory. Okay, all right. All right, so you have the group and you have the tangent space, you have the exponential map connecting them. What we would like is some extra algebraic structure on the tangent space, which would have some connection with the group operations. Okay, and some linear sort of further operation on the tangent space, which is connected with the group operations. Okay, and that would then really be helpful. So we need something like that. And I'm just going to tell you what it is, but some sort of mild motivation can come from this discussion. Right? We saw that whether things commute with each other or not seems to matter and affects how well, just how tightly the exponential binds the tangent space to the group, right? So whether this AB is equal to B, or another way of saying that, whether AB minus BA is 0 or not is important. Now, once you have something like that, that whether something is 0 or not, naturally you should study that thing itself in general, and then you can sometimes study what happens when it is 0 and when is it 0, etc. Okay. All right, so define the following thing. Let's simply take xy minus yx. Okay. So what is this? This is giving a map, right? So you can take any two n cross n matrices and you can apply this bracket operation to them, right? And that will measure the extent to which they commute with each other. And you will again get an n cross n matrix. So it's a map from this product to this, right? It's a binary operation on ML. Okay. You can see that if you vary x linearly, then the result will vary linearly. Right? If I double x, the result will double. If I take x plus x prime here, then I'll get xy plus x prime y. Okay, because you get x plus x prime, x plus y prime, you can distribute, open up. So one thing that you can see is that this is bilinear. Okay. What else can we see about it? Well, as soon as you have a binary operation, you wonder, right? Is it commutative? Is it associative? Now, what will happen if I switch x and y, right? It will become yx minus xy. It will become the negative of what it was. So it's not commutative, but it is something like commutative, right? You get a minus sign, okay? Another way of saying the same thing really is that anything bracketed with itself is 0, right? You can also observe that. So this is called skew commutativity or anti-commutativity for this bracket. Now you could also wonder whether there is something like associativity, and again, this bracket is not associative, okay? But there is something a bit like associativity, okay? Not too much, but you can see that it has something of the same theme. So what's associativity? That if you have ABC and you first combine AB, or as you first combine BC, you wonder if it matters. Here it will matter in general, okay? But here is, now because you have an explicit formula, I'll just write the result. But if you're curious about whether it's true, you just have to blow up the left side and the right side according to this definition and see that they match. Well, I'm only going to put a left side. So here is the interesting thing, x, y, z. Right? You have 3. You could pair these two and then with x. And then a certain cyclic pattern. So what's happening here? Right? You move the z to the front, you move the x here and the y here, okay? And then you repeat. So now the y will go to the front, and then the z will move here and the x will move here. And funnily, when you do all these things, the answer is 0. Okay. This is called the Jacobi identity. Okay, so you have this bracket, right? And we have some idea why we should study it. And these are the main algebraic properties that this bracket has. Okay. Okay. All right, now it works on Mn. Naturally, the question is that if I'm going to move to a subgroup and the corresponding subspace, is this bracket going to be present there also? Okay. Now I can, you can take this tangent space little g, and its members are n cross n matrices. So you can certainly take the bracket. But the question is whether that bracket will again end up in the tangent space or not. But let me just first introduce one term, okay? So a Lie algebra is basically something like we have just talked about, is a vector space, okay, with a map, right, binary operations, which have these three properties, which is bilinear, skew commutative, and has the Jacobi identity. Okay. Okay. So the whole question is this going to be a useful concept for our matrix group? It's a useful concept for GLN because Mn that we had for it is a Lie algebra under the bracket that we saw. Okay. But the question is, what about if I take any matrix group? So here's a nice theorem. Okay. G is a matrix group. And you take the tangent space at identity. Then in fact, that is a Lie algebra. Under the bracket that we are working with. Okay. For an abstract vector space, there may be other ways of coming up with something with these properties. In fact, you have seen one in school. Okay. And maybe this cyclic kind of property you might remember from school. Do you remember? Does it remind you of something? Some way of combining two vectors that had a property like this? Anybody?
The cross product.
Yeah. Yeah, the cross product. I mean, how many ways of combining vectors did you learn? Dot product and cross product, right? Dot product doesn't give you a vector back. So the answer better be the cross product. And the cross product is exactly like this, right? If you take V cross W, or you take W cross V, remember there's a change in sign, and there is exactly this identity as well for the cross product. U cross in bracket V cross W plus equal to 0. Okay. So for instance, that is a Lie algebra. So three-dimensional space with the vector cross product is one basic example of an interesting Lie algebra. Okay. Okay. All right, so here's a theorem. We need to prove this. Now this bracket already has all the right properties. So really the only issue is of whether the Lie algebra is closed under this bracket or not. Okay. If it is, then it will become a Lie algebra under this bracket. Okay, now if I take some x and y which are in this tangent space, then they are coming from some curves. So take those curves. So they have to pass through identity at 0, because we are looking at the tangent space at identity, and then the derivative should match the vectors that we have been given. Okay, so suppose things are like this. Okay. Okay, now I need to create some curve whose tangent vector will be xy minus yx. Okay. All right, now this is going to be a little involved. Okay, and I can't really motivate it too well. But once you are in this subject, then the kind of thing that I'm going to do, you become used to it and you start thinking about it yourself. I mean, you can figure out yourself that this is the sort of thing I should do. So what we're going to do is we're going to create a certain function of two real numbers, s and t, which will be some combination of alpha and beta. Okay. So it will be alpha s and beta t and alpha s inverse. You can perhaps have some idea of why I should have an inverse. That's going to create the minus sign that I want, and I should work with some product like this so that when I differentiate and apply product rule, I should get, I should get a sum, right? But for the minus sign, I'm putting an inverse. That is some partial justification for looking at an expression like this. Okay. So first I do this. Okay, I've set up a certain function. This is not yet a curve because it depends on two real numbers rather than one real number. Okay, but fix the first one for a while. Okay, and then use with that s fixed, define a certain curve gamma s. Okay, to g by simply taking the value of fst. So you're basically taking fst but keeping s fixed and only varying t. So that will be a curve, right? Okay, and the quill, right? And then what kind of curve is it in G? So what is the value at 0? So let's put t equal to 0. So this will become identity. And alpha s inverse will become identity. So that's good. This curve is passing through identity when the parameter is 0. And the other thing is what happens if I differentiate it. Okay, well, right now the alpha s and alpha s inverse are constant. So you simply need to differentiate this middle term and you will get beta dot 0. Beta dot 0 is y. So this will become alpha s y alpha s inverse. Okay. All right, so that is a tangent vector. And now this is a curve in G and this is its derivative. So therefore this is a tangent vector, right? So this is a member of a tangent space. Okay. All right, now what have I got, right? If I look at this expression and I say I'm going to vary s, then what have I created? I have created a curve in this vector space little g. Now when you have, right, and that's basically a Euclidean space, right? A finite dimensional vector space. Now in a Euclidean space, if you take a curve and you differentiate, where does that vector lie? It lies in the same space. Okay. So if I were to now take this curve and differentiate this curve, the result would still lie in G. Okay. All right. Now the thing is I have to, therefore, this is going to be the one we want. Okay, but how do I differentiate this? I'll apply product rule. Once I'll differentiate alpha s, once I'll differentiate alpha s inverse. Now here things get a little tricky. I know what is the derivative of alpha s, right? It will be my x, but what's the derivative of alpha s inverse? Well, I need to find that. So to find that, let's backtrack, right? And say, okay, what is alpha s inverse? Well, This is the defining equation for alpha S inverse. So if I differentiate both sides with respect to S. Okay. And you get the derivative of this guy, and I is constant, so derivative is 0. Now you can solve for this, right? So you have to bring this to the other side, you'll get a minus, and then P multiplied by alpha S inverse. Minus sign. Okay. Okay, good. So we now know how to differentiate the inverse. So we can go back to our main argument and we can compute this. Let's just give it some name Z so that I just write that Z. Okay, so what you have to do, you have to differentiate first the first term with respect to S and then put S equal to 0 in the whole thing. So this will become alpha prime S, and then you will put S equal to 0, alpha prime 0. That was your X, and then you have Y. And when you put S equal to 0, this is identity inverse. So that's just identity. So you just get XY from the first term. What you get from the second term, you will be differentiating this one. And so here you put S equal to 0, alpha 0 becomes identity. And you have this Y. And then you have the derivative of this. And here is the derivative, okay? And you need it at S equals 0. Now, if you put S equals 0 here, this first, so you have a minus, and this first term is identity. Alpha prime 0 is X, and the last term is just alpha, right? Identity again. And there you go, you have got X5 minus YX, okay? And this thing belongs to G, so therefore X5 minus YX belongs, okay? So there's a bit of, okay, it's a clever trick. I can't really easily justify it, you know, in a quick manner, but one has to kind of, well, actually, if one understands the exponential function a bit more and see how the tricks work, one becomes used to this sort of conjugation and playing around with the parameters. So, I mean, that's what's happened to me, and I don't really have a better answer for you than that. Okay. All right. So now we are getting somewhere. We have, you know, now we have a good situation. We have, if you have a matrix group and identity, then you have a tangent space, and you have a map, exponential map, which is a local diffeomorphism. Okay. But also now, this G is not just a vector space, right? G is now a Lie algebra. It's closed under a certain bracket, and that bracket has something to do with the group operation. Okay. All right. Now there are two directions I should go in, okay, give you a little taste. One is I should show you a sort of abstract result that can come out of such, you know, that can show you how you might sometimes be able to get knowledge about the group structure from knowing the structure of the associated Lie algebra. And the other is that given a group, can we easily find out what its Lie algebra is, right? Okay, so there are these two aspects. Can you find out what the Lie algebra is? Okay, only then you can work with it. And if you can work with it, what kind of observations about the Lie algebra might tell you something about the matrix group? Okay. All right, here's an interesting theorem. So let G be a matrix group and let it be connected. Now, one thing that happens is that the Lie algebra is mostly useful for telling you about the matrix group when the matrix group is connected. Or else if the matrix group is not connected, then it has multiple components. then the Lie algebra is only good for telling you what's happening in the component that contains the identity. Okay, so that is what it connects with. It's not able to tell you directly about what's happening else. And now, so anyway, you have a group in front of you, and one of the basic questions you ask for a group is it abelian or not? Right? And the claim is that G is abelian if and only if the bracket on the tangent space is trivial. Trivial means that no matter what tangent things you look at, the bracket always turns out to be 0. Okay, so that's called a trivial bracket when it's just 0 always. Okay. So essentially, if things in the Lie algebra commute, then things in the group commute. Okay, I will do this both ways. Let's suppose G is abelian. Well, in fact, the proof that we just did, I mean, this is interesting. We will actually look at that proof and say, well, okay, we saw G is a Lie algebra, but we actually learned something about the bracket. We got the bracket in a particular way. Maybe we can use that to figure out what the bracket is, right? Okay, so consult the proof that we just did. Let's go back and consult it. So I've created this FST, I've done something with it. Now suppose the group is abelian. And what will happen to this map FST if the group is abelian? Yeah? Someone?
Constant in S.
Yeah, I mean, right. So what will happen is since they can commute, the alpha S inverse can come to the left and can multiply the alpha S and cancel it. So you'll just have beta T, right? So all your gamma S's are the same, right? They're all beta T. Okay. Okay. And therefore, all these things that we computed, all these gamma S dots that we computed, they are all the same. As I vary S. And how did I get this xy minus yx? By differentiating this curve. But if this is constant, what will be its derivative? 0, right? Derivative of a constant will be 0. Okay, so there you go. So therefore, bracket of xy, which in my proof was the derivative of these guys, because this was a curve in G, and so we differentiated it. Since this is constant, this will be 0. Okay, so that's the proof that if the group is going to be abelian, then the Lie algebra better be abelian, the bracket just be trivial. Okay, xy equal to yx. And let's do it now the other way. So suppose that it's the Lie algebra which is abelian. So one says the Lie algebra is abelian if the bracket is identically 0. Okay. And so that's natural. It's kind of matching up with the group being abelian. Okay. So now suppose G is abelian. Okay. So that means that given any xy in G, xy will be equal to yx. Now, what do we know about that? We know that if that happens, then e to the x and e to the y is e to the x plus y. And that is, of course, ey, ex, right? By this. So the corresponding group elements will commute. Okay. So anything in the group, things in the group which are images of, the exponential map will commute with each other. That doesn't by itself establish that the group is abelian, because exponential actually may not be onto. Okay. If the exponential was onto, then this would finish the proof, right? Then everything would look like e to the x, e to the y, and therefore would commute with each other. But exponential need not be onto. Okay, in fairly simple groups, it fails to be onto. So we can't finish the proof like that, but we will do something. Okay, let's use what we have. Now remember that, but at least I know this, that in the group, there is one open neighborhood at least, right? Which comes completely from exponential. So there is an open neighborhood V of identity, in which everything is an exponential, right? Okay. And therefore, at least everything in this neighborhood will commute with each other, but we don't yet know what happens to things further away. Okay, but if things in this neighborhood commute with each other, anything in the subgroup generated by this set will also commute with each other, right? If A, B commute with each other and you create expressions like A, B square and A square, B inverse, then they will also commute with each other if A and B commute. So how do I, describe all the things I can get like this? Well, here is one way to do it. I will use V to the n to stand for an expression which is made by multiplying n things, each one of which is from V, right? And I want to take one thing or two things or three things or four things, and I want to do this in all possible ways. So I want to take the union. And I want to call this, say, H. Okay. Now V is open. Okay. Now one can prove from that V square will be open, V cube will be open, etc. And therefore all the Vn's are open, so then the union is open. Okay, so that's one thing that we can do. The other thing is that this is basically the subgroup generated by V, right? So this is in fact a subgroup of G. So it's an open subgroup of G. Okay. Now it turns out that open subgroups are very special, also very rare, and you will soon see why. Okay. Now let's think about this, the fact that it's an open subgroup. Okay. So take your G, and let me just take G, and let's suppose this was some H, right? Then I take all the cosets of H. Okay. Now H is open. Multiplying by a constant, that's a continuous map. And it has an inverse, multiplying by the inverse of that constant. Okay. That means that if H is open, then constant times H will be open. So all these cosets are also open. Okay. Now let's look at all the cosets which are not H. Let's look at all these cosets. All these are individually open. What about the union? What about this blue portion completely? All the cosets of H except H itself. Can you say something? Is this a closed set, an open set, or we can't say anything?
An open set.
It will be open, right? Because union, any union of open sets is open. Now, if everything else forms an open set, then what kind of set is H?
Closed.
H is closed. Now, this is a completely general fact, right? It has nothing to do with this particular H. If you look at this, what we have just learned is that if you have a matrix group and you have an open subgroup, that open subgroup is automatically closed. Okay. But coming back to this situation, I had a connected group. I have a subgroup which is open and closed. What must happen? In a connected space,
Is it empty or the whole space?
Yeah, it has to be the full thing, right? That's the only way out. Therefore, H is equal to G. But this H is of course abelian because it's made of things which commute with each other, and therefore G is abelian. Okay, anyway, so even though we are doing kind of basic things, in these lectures, but I hope you see, sort of the richness, right? I mean, this is the kind of thing that attracts me to this topic. There's a group and you're asking an algebra question whether the group is abelian or not. But to do it, we are looking at differentiable curves, we are looking at the tangent vectors, we are looking a final look at how the vectors integrate, interact, the Lie bracket. Right, we are looking at the subgroups, open and close, their properties. So we are looking at topology, at analysis, right? And all this is coming together to help us out with the question which originally is actually a pure algebra question. Okay, so that's an example of how knowledge about, how linear algebra could be useful in solving some group, right? Because whether the bracket is trivial or not is a linear algebra question. You're doing something in a vector space with a bilinear map, right? But the consequence is for the structure of a group and whether that group is an abelian group or not. And so there are more advanced, results of a similar flavor for other questions that you could ask about the structure of a matrix group. You sort of have corresponding questions that you create for the Lie algebra, where you solve it using linear algebra, and then you come back and say, therefore, I have learned something about the original group. Okay. Okay, now that was an abstract thing, but another thing we should do is, I said that, where was it? Yeah, this, right? That I have a way of identifying the Lie algebra of a Lie group. By this, let's see that this is actually a practically useful criterion, okay? Now we know only a couple of matrix groups, but let's work with them. GLN, we anyway know the tangent space, it's Mn, but what about SLN? Can we find out its tangent space? What about ON? Can we find out its tangent space, okay? So we can with the help of this theorem. Yeah. So let's do an example. Take G to be SLNR, right? Matrices with determinant equal to 1. Okay. Now remember, so now there's a tangent space at identity. Right now I know nothing about it. And there is some X, I wonder whether it belongs to that or not. But I have a criterion. If and only if all these exponentials belong to G, right? Okay. Now when will they belong to G? If the determinant is 1. Okay, so for every T this should happen. What did I know about determinant? That it is exponential of the trace. But this is exponential of a real number. When can exponential of a real number be 1 for every T? Okay, well, yeah. So when can this exponential be 1? If this real number is 0, right? That's the only way it can be 1. Okay, and in this T I can pull out. So T times trace of X needs to be 0 for every T. How can that happen? This trace needs to be 0, yeah? Okay, so there you go. We have exactly identified the members of the tangent space of this matrix group, right? We have found that G consists of those members of Mn whose trace is 0. Okay. And incidentally, so there's a standard name. You have this sort of notation. So capital G for a group, then little g for its Lie algebra. So if the name is SLN with capital N and S and L, then the natural name for the corresponding Lie algebra is this with small SLN. Okay, small s and small l. Usually written in some fancy script, but okay, I can't do that by hand. Okay, so we were able to, also identify the tangent space, and so it's a very concretely known tangent space, right? If I have to do some computations in this space, it would not be, hopefully not be difficult. Let's do another example. Okay. The only other example we really have even talked about is ON. So let's look at that. Okay. These are the n-cross and orthogonal matrices. All right, let's do the same thing. Let's start the same way, but this is slightly more subtle. So when will X belong to the Lie algebra of this one? Again, just put down the result that e to the tx needs to belong to G for every real t. Now, when will that happen? That means this needs to be an orthogonal matrix, right? So e to the tx transpose times e to the tx needs to be the identity matrix. Okay. All right. Now, when you take, now remember this is power series. When you take transpose, what will happen? You will simply end up taking the transpose of every term. And in any term, if you have transpose of x to the n, that is simply the nth power of x transpose. So it's not hard to see. I mean, I've already told you the steps, that this is simply the exponential of x transpose, basically. Okay. All right, now I'm stuck, yes. Why am I stuck? Because I don't know whether I can merge these into a single exponential and then get something. Okay. Well, now what one should do in such situation is say, okay, suppose I could bring them together, right? So let's fish around and see if we can make something happen. When would I be able to convert this into a single exponential? If x and x transpose were commuting with each other. Okay. They may not, right? A matrix may not commute with its transpose. So we'll fish around. We'll say, all right, when they do commute, can we figure out something? Okay.
So,
yeah.
But they are inverses of each other, so they must commute.
Who are?
Oh, sorry.
Okay, no, the question is different, right? Question is not whether these exponentials commute with each other, but whether I can write this as a single exponential. Okay. All right, so let's just fish around. Suppose x and xt commute. What would we be able to say then? Then this would merge into a single thing. Okay. It would become this for all t. Okay. Now is there anything that occurs to us now that when this can happen for all t? Well, you see, remember what happens, I mean, this is a curve, right? which is constant. So if I differentiate it, I'll get 0. Okay. So if I differentiate this, I'll get 0. But what is the derivative of this, right? The derivative of this is just x plus x transpose. Okay. All right, so we have learned that if they were to commute, then x plus x transpose would have to be 0. On the other hand, if x plus x transpose is 0, they would have commuted, right? I mean, obviously, yeah, then x transpose would just be minus x, and minus x, of course, commute with each other. So can I claim this? I want to make a certain statement and tell me if I have done all the necessary work already or not. Okay. I claim that this is the Lie algebra that I want. Anybody wants to say I haven't proved it? You should, okay. Suppose I tell you that you should say that I haven't proved it, then can you tell me why I haven't proved it?
Is it about the smoothness of the curve?
Sorry, no, smoothness is not an issue.
Or why the derivative is indeed this? Because you're looking at
That
the
is also fine. Derivative of e to the ta is a.
Okay, but there could be matrices. Like if x and x transpose don't commute, then we don't know if.
So what I have actually proved is that actually what the matrices that I have taken, they certainly belong to the Lie algebra. The matrices with x plus x transpose equal to 0, they will certainly belong to the Lie algebra, right? Okay. Because if x plus x transpose is 0, then x transpose is minus x, so x and x transpose commute. I can, well, I mean, if x transpose is minus x, I think you can see that thing will work and the thing will always be in the right place. But the issue is, what if, is it possible for this to be satisfied without this, right? Now I discovered it by looking at the commuting case, but potentially some non-commuting thing could also, have this, right? Equal to I for all t. Is that right? I mean, maybe, so who knows? So maybe some non-commuting thing, you could still have this thing satisfied. I have certainly not ruled it out today. Okay, so I think let it go at this because this is finally the right answer, even though what I've done today is a little incomplete. Okay, I feel that what I have really established is that x plus x transpose equal to 0 is part of what I wanted, not necessarily that it is all that I wanted. Now, there are many other finer things about exponential which we haven't done and which I think would have been useful in polishing this off. Okay, or maybe I'm just not clever enough today, but never mind. So the point is that these are the kind of things that we do, okay, with groups and the corresponding algebras using criterion like this. For most groups, one can actually give explicit descriptions of the Lie algebra. Okay, and then this is an example of how knowledge about the algebra might tell you something about the group. Okay, let me just give you one last big theorem. Okay, just so you see that how nice a setup this is. Okay, so here, so far we have been talking about a single group and its Lie algebra, right? But you are not always interested in just a single group. You are interested in relations between groups, right? You're interested in, there's a homomorphism between two groups. What can it tell you? And so even for questions like that, we would want to know if this approach helps, right? So if I have a homomorphism between two groups, can I convert that to something between the two tangent spaces? Okay. And then if I know something about one tangent space, then can I learn something about the other tangent space, and then from that learn something about the other group? Okay, so I have a different way of acquiring knowledge about going from one group to another, not directly, but through the tangent spaces. Okay, so there is a theorem which lets us do that. Okay, and I just want to state it. So suppose that G and H are matrix groups. And you have a homomorphism, a matrix group homomorphism. Okay. So that means, remember, it's continuous and the image is closed. Now, here are some remarkable things. One of them may really be a bit shocking, and the others are sort of structural and, you know, on a familiar pattern. Okay. So this is the one that's a bit shocking to me always. Here are two groups. I gave you a function which was continuous. And the remarkable thing is it's automatically going to be differentiable. Okay. Of course, it's not just any old function. It's a continuous, it's a group homomorphism. So continuous group homomorphisms in this context are automatically differentiable, right? So that's very rare and surprising that continuity should take you straight to differentiability. Okay. All right, now once it's differentiable, then we can have an interesting thing, right? I have this from G to H. And for G, I have the, yeah.
Are you writing something? Because I can see in the screen claim of X belongs to M.
Yeah. Okay, yeah, I don't know. It suddenly said your screen sharing is paused. Okay, that's interesting. I wonder how that happened.
You can unshare and again share maybe.
Yeah, just a second.
Since there is a gap, so I think earlier problem we can differentiate on both sides, right?
Hang on. Okay, let me stop this share properly. And now let me start again. Okay,
Yeah,
how is it now? Okay.
Yeah, now
Yeah.
we can see. Yeah.
So how long ago did this happen?
So you just started a theorem and then
Okay.
yeah.
Okay, so not so bad. All right, so theorem is this. Okay, so there are two matrix groups. There's a matrix group homomorphism, and the first one is, I think, surprising that automatically this continuous homomorphism turns out is, I mean, it just has to be differential. Okay. All right, then going on, right, as far as the group goes, we are hoping to understand it through its tangent space at identity through the exponential map. And we are hoping to understand H, right? And so I will use this symbol, this little h, for the tangent space to this thing at identity, and it has its own exponential map like this. Okay. Now, when you have, remember what we did already. So if you have a function of several variables, then the derivative is a linear map between the corresponding vector spaces, right? Here the corresponding vector spaces are G and H. And so you can set up the differentiable, the derivative like this from this linear algebra to this linear algebra. Okay, I'll give you the definition. But the main thing is going to be, I'll just give you the definition in a second. But the way I started writing this, after this diagram, I want to tell you that this diagram commutes, right? So if you start from here and go like this or go like this, you'll end up in the same place. Okay. All right, but what is d pi? So I have to tell you what d pi does to some x here. Okay. So this is again that same thing that we had, that you basically take the directional derivative, but now we will do it using this exponential map. So what we will do is we will take exponentials of t to tx. Now that will be a curve in G, right? X is in G, so all the tx are in this Lie algebra. So the exponential is in the group. So now you have a curve here. You apply pi, you get a curve here. How can you get something here? By differentiating that curve. So you take this and you differentiate, right? So that's the natural thing to do. And we have, so this is a commuting diagram. Moreover, this d pi is a Lie algebra homomorphism. What does that mean? That means, as always for a homomorphism, that it preserves whatever structure you are looking at. So if you were to take d pi and act it on some bracket, it would be like taking the individual d pi's and then taking the bracket. Okay. Okay, so every group homomorphism has a corresponding Lie algebra homomorphism. And so this way, if you understand the theory of Lie algebras, it can tell you something about the theory of groups, not just for an individual group at a time, but even when you are studying the connections between groups. Okay, so I think let me stop here and let me show you some references, right, for further reading. So I'll just show you a couple of slides with some book names on them. Okay, so if you have found this sort of interesting, then there are various books which you can take up either at the same level or at a slightly more advanced level. And let me show you a few books of that type, right? Okay. Now, Artin's book on algebra, I think, is fairly well known, right? And it's a book that does, group theory with a good interaction with linear algebra. So that's the sort of thing that we are also doing. And some of the things we have been doing today, you will find in Artin's book. And of course, he has always an interesting way to explain things. Okay, and then there is this book by Smirnov. It's a Russian book, but it's in Dover. It's not really expensive. So this also has a portion on linear groups, right? You can see that's the structure also, that he first developed linear algebra. so that when he does group theory, he can use these kinds of examples. Okay, there's this really nice book by two Russian authors that AMS had got translated and published, but then in India it's been published by Universities Press on transformation groups. So these matrix groups that we are talking about, they're also called transformation groups because they're made of linear transformation, right? The matrix gives you a linear transformation, and sometimes it's useful to have that abstract viewpoint rather than the concrete matrix viewpoint. Transformation groups for beginners, it starts with more elementary things, certain symmetries and so forth, and builds up. Okay. So these are sort of at the more basic level.
Sir, naive Lie theory by John Stilwell. Yeah. Okay.
Okay. So yeah. Okay. And so here are four more. I don't know why I didn't have the cover for the fourth one. Yeah, so John Stilwell's naive Lie theory is very much, the sort of thing we have done today, and with very nice examples and pictures. It's an example-oriented kind of book. And similarly, Christopher Tapp, Matrix Groups for Undergraduates. All right. The book by S.C. Baki, Shobha Madan, Ladi Sitaram, U.B. Tiwari, this thin book on representation theory and linear Lie groups. So again, it's one of those things. Representation theory is a vast subject that you can do with finite groups or Lie groups or anything else. So there is a very interesting sort of theory for Lie groups. But again, the idea that they had was that why not work out things for linear Lie groups, right? Where things will be more concrete. So it's a very nice little book on linear Lie groups. And in this, then the representation theory that you have also links up quite heavily with a bit more abstract analysis, with analysis that involves a bit of measure theory and things like that. So it starts becoming more of a master's level text. Okay. And I think Andrew Baker is maybe of the same line as Christopher Tapp, but just a much more detailed and heavier book, taking the subject to a more advanced. But these are all books that if you are, third year undergrad or master's student, I mean, these should all be accessible to you. If you're looking for some advanced reading course or projects, you could consult one of these books or more of these books and have something nice to do. Okay, so I think that's where I'll stop.
Thank you, Professor Habib, for such a nice introduction and talk. So anyone has a question, you may raise your hand or write down your question over chat.
So no one. Sir, might have one comment, sir.
Yeah.
In that earlier that O(n) O of n.
Oh.
So x plus x. So we can take a differentiation product rule and p equal to 0. I think it will work.
Oh, okay. So just take the product and just differentiate without trying to merge.
Right.
Yeah, okay.
And then t equal to 0.
Right.
Yeah.
Okay. Thanks.
Yeah, Ishan want to ask something. Ishan, you may.
Yes, please. Thank you. First thing is, when you're defining a matrix group, where are you used? Why do you want it to be a closed subgroup? That's one. And the second thing is, for that ON thing, I was thinking instead of taking the exponential map, maybe you can take the x times x transpose is equal to the identity and differentiate that. Take that as a smooth curve.
Okay, but different, I mean, what is the thing with respect to which you are differentiating?
I'm treating it as a map. I don't know. I was treating it as a
Wait,
map.
what's the variable now when you are differentiating?
Yes. Yeah. So I was treating it as a map between manifolds from MNR to.
I don't know what a manifold is.
I wasn't sure if I should say
Yeah,
this.
today I don't know what a manifold is. And in any case, whatever you want to say with manifold, you should be able to say in this language.
Okay, I will try.
Yeah.
Could you tell me about the closed thing?
Yeah, okay. So I think, it's basically if you want sort of the overall package to have some consistency. So for example, suppose, suppose you want to quotient, okay? So let's say you have two groups, you have a group and you have a subgroup, and you want to quotient. The group had a topology, so the subgroup has a topology, and there will be the quotient topology on say G mod H when you do that, okay? Now suppose I want G mod H to be a matrix group. Do I have any chance at all? Okay. Suppose G was a matrix group and I want my G by H to be a matrix group. If that's the collection I'm working with, I want some chance of that happening. Okay. Now here's a funny result that G by H will be Hausdorff if and only if H is closed in G. So if you work with things which are not closed, your quotients have no chance of being Hausdorff, and can't be Hausdorff, but definitely then not be matrix groups. Okay, so that is so, and there are other things like that. So basically, keeping it closed keeps sort of this sort of thing nice, working with closed groups. Okay, and similarly, you want to learn things by differentiating, right? So in some sense, your limit things need to be present. Taking limits is not a nice thing to do.
Okay, thank you.
Anyone else?
Omkar raised hand.
Also, there are, in the bigger theory, closed has many, has one particular important thing. So you said this word manifold. Okay, let me take it up now. Okay, because it's not about what I did in the lecture. Okay, so that would be the more general thing. See, think of what groups did we do, right? So GLN, it's locally just MN. Now SLN, I have not really told you, but the circle group is locally one-dimensional and so forth. So you could ask whether these matrix groups are going to be manifold. So this is for people who know what a manifold is. Okay. And there's in the abstract setup, there's a nice theorem that says that if you work with a closed subgroup of GLN, automatically going to be a manifold. Okay. So there are many such things that is automatically going to be a Lie group. So closed things just have many nice things associated with them. Okay, that doesn't mean you should always ask for things to be closed, but when you are trying to set up some basic, consistent, complete theory, it's a good assumption to have.
So the closed thing is allowing for a subgroup to be a Lie group. Okay.
Or the matrix group itself. Why should a group made of matrices be a Lie group? There's no reason. If it's closed, it will be.
Okay, thank you. So every matrix group which is closed becomes a Lie group.
Look it up in the text.
Okay.
Yeah. So there are some remarkable, surprising things in this. Yeah. Okay. So I think that.
Any comment? If there are no questions, comment. Anyone more? Omkar, you raised your hand. You want to say?
Actually, it was the same thing that Satya sir said. I was not sure of the product rule. So what I thought is, since this e raised to tx is invertible, and since minus tx commutes with tx, you can post multiply that equation with e raised to minus tx and then differentiate. So you'll get x to the t equal to minus of x. Sorry, x transpose equal to minus of same.
Yeah. Sorry, I was just checking. So what Satya said was perfect. Of course. Should I write it out? Okay, so in that ON thing, Satya was pointed out that there's no need to digress like I did. Just work with the thing that you had in hand, and you ask, what do you need? So you need this to always be I, right? And so just, okay, so let's see, so you differentiate, let's see what will happen. So you apply the product rule. Now in this one, the X transpose will come down and then you will have the exponential. But at t equals 0, everything else becomes identity. So you will just have this. When you differentiate this one, you will just get that X. And when you put t equals 0, all the exponentials will become identity. And I will have this, but still, Satya, okay, now this is for all t and this implies this. So this is true. Okay, right. So X belongs to G implies this, right? And I had also told you that why this, anything set this would be there. Okay, so therefore things work. Okay, so actually there are two halves. I did it one way, one half, and what Satya is saying will exactly fill the other half. That so if something belongs to the Lie algebra, it must satisfy this X transpose plus X equals 0. What I proved was that if X transpose plus X is 0, then it must belong to the Lie algebra. Okay.
Okay, so I think there are no questions. So
It's fine.
yeah,
Can I
Let's stop here then.
recording? Yeah, I stop.
I will stop video and mute myself. Thank you, Karan.
So, Priya, you want to say something? Then I will stop recording. Huh?
Yes, sir.
Okay.
Somebody raised hand.
Ishan, you go ahead.
Yes, please. I haven't checked. Are these notes available somewhere? The ones that you wrote?
I mean, right now they're available with me.
No, I mean,
And I wrote them.
Okay. No, I meant that will you be sharing them somewhere?
I mean, okay, I mean, it's up. If Karili wants, I can give them. If you want, you write to me and ask.
Okay. Thank you.
There's nothing secret about them. Okay. Okay, Priya.
So, sir, this was a wonderful session. So, on behalf of Leaf and MTTS Trust, I thank Professor Amber Habib for accepting our invitation and taking time from us busy schedule to deliver this session. And also, I thank Professor Pradip and Professor Satyanarayana Reddy for chairing the sessions. And we are very grateful for your support and guidance. And I also thank all the participants for your active participation. And I thank MTTS Trust for sponsoring this event. So thank you very much.
Thanks. Take care, everyone.
Thank you.
So we can take a group photo. So if, so we can turn the video on the participant.